wave function, which has a certain, L value, right? The L value is the orbital momentum, quantum number. So depending on what L the electron has, and what its projections are for S, its spin, it could actually have different combinations of angular momentum. So what that lecture was trying to say is, we can make now combinations of spin and orbital angular momentum in a variety of ways, and therefore we have different so-called spin-orbit coupling scenarios. Okay? This is important for us in terms of the hydrogen atom. The example that the lecture ended with is that if you have an electron that I'm exciting from the 1s, its ground state, to the 2p state, that's an excited state. Okay, so this is the ground state, I'm exciting it to another state, that is the 2p state. In the 2p state, the electron has orbital angular momentum because L equals 1. It also has spin. Okay? So, but the spin can have different projections. It can have negative half and plus half, spin up, spin down, alpha, beta. And therefore, the total angular momentum can be a combination of these two things, the L and the S. One way to think about it, and it's not exactly right, but we'll get to it, is that if I have L equals 1, I can just have my spin make the angular momentum bigger, so it's going to be 3 halves, or L minus half is going to be 1 half. So the total angular momentum that the electron can be 3 halves or 1 half. So basically there's two different scenarios, two different angular momentum, total angular momentum quantum numbers that the electron can have. 3 halves and 1 half. These are two different quantum mechanical states that the electron can occupy. Okay? So that is also what we will see here. So this is kind of like somewhat of a summary, I guess, of our scenario of the electron in the hydrogen atom. These are all kinds of states that we have solved by solving the Schrödinger equation. So these are the wave functions. The wave functions, of course, represent the orbitals. Okay? And these orbitals, they have different energies. The lowest one, this guy, is psi 1, 0, 0. That's the ground state. It has a certain energy. The energy here is indicated in kind of a shorthand notation. Okay? It's written as hc RH divided by n squared. N squared is a principal quantum number, that's the main thing, so n is changing. And then there's a bunch of constants up on top in the numerator. H, C, you know what they are, and then RH, maybe you haven't seen that one, but that is the Reupload constant. Okay? The Reupload constant. So, it's given as this, so basically it's just the collection of these natural constants that we have seen before, just grouped together and given a name, RH. It's way easier to write RH than write all those things every time. Okay? So that's why it's helpful to have this shorthand notation. HCRH divided by n squared. You can see then in the lowest state has, because n equals 1, is just the value negative HCRH. Why is there a negative sign here? What does it mean? Does it mean the energy is negative? It's kind of weird. How can you have negative energy? Who knows what that means?
Stable.
Negative is stable? Say what? Yeah. Okay, look. If you go all the way to the top, okay, of this diagram, so that will basically be, I'm increasing n squared, but the n squared is in the denominator. So when n squared goes all the way to infinity, you can see it all the way to the right top, n equals infinity. Then E is 0. Okay? So that's, the electron has 0 energy. So what that means is, if the electron is bound to the atom, if it's part of the atom, then this negative sign indicates the binding energy that it has. Okay? In other words, if you want to kick the electron out, if the electron sits in this state and I want to get it out of the atom, I have to basically give this much energy with a plus sign to get it out. That's the amount of energy you have to put in to kind of dislock or unlock the electron from the atom. That will be the ionization energy needed. The negative sign means that it's bound. If you want to unbound it, you have to put energy into it. That's going to be a positive number. That's why this is a negative number. So it's kind of convention, okay? It's not real negative energy, but it's the energy that we need to put into it to get it out. All right, and you can see if you're in the lowest state here, you have to put a lot of energy in. If you are in higher states, so when n goes up to a higher number, I have to put less and less energy into my system to kind of get the electron out. The ionization energy of the electron in the hydrogen atom, therefore, is the same number as this with the plus sign, HCRH. That whole energy here, HCRH, that is called the Reupload energy. RH itself is called the Reupload constant. If you put HC in front of it, it's called the Reupload energy. The Reupload energy is the ionization energy of the electron in the hydrogen atom. Okay? And the beautiful thing is that if these are all natural constants, I can just fill it out. I can calculate what the Reupload energy is. I can predict, based on this quantum mechanical model, exactly how much energy I need to put in to get the electron out, to ionize the atom. It is absolutely a perfect number. It really is in concert with the actual measured value. Okay, here it is. That is the value. Now with the plus sign, because that's the energy you have to put in, 2.18 times 10 to the minus 18 joules. Okay, that's the ionization energy of the hydrogen atom. This is a number, a good number, or a good order of magnitude to have in your mind, because that is the order by which electrons are bound to atoms. Okay, so this, if you are asked to calculate things of that nature, you should be in this range. If you're way out of this range, then maybe you did something wrong in computation. Always keep track of what you expect the numerical value to be. Yes?
So it's the ionization energy for an electron in the s orbital,
Yes. If the electron occupies, or the electron is described by this wave function, the ground state of the hydrogen atom, then you have to put this much energy in to get it out. Okay, now, this is what lecture 14 talked about. It says, wait a minute, there are two possibilities of combining the angular momentum of the electron when it sits in the 2p1 state. The 2p1 state is now when I'm exciting it from the ground state to a higher state, n equals 2, and we'll go into the p state, as you will see in a moment. So the electron configuration is 2p1. It doesn't sit in the ground state anymore. The electron now sits in the 2p state. There's 3 of them, but it doesn't matter which one at the moment. Just one of the 3 p states, that's where the electron sits. If it sits in that state, it can occupy 2 different scenarios, 2 possibilities that represent 2 different ways in which the angular momenta can be combined. One of them is 3/2, that's the subscript with the p. That's one way in which you combine the angular momentum. The other way was 1/2. This is what lecture 14 says. We're using it here. So instead of writing 2p1, that's just one possibility, there's actually 2 possibilities, 2 angular momenta combinations that we have to contend with. And the electron can be either in the lower state or in the higher state of these 2 possibilities. This split is called spin-orbit splitting. Spin-orbit coupling, splitting. The energy is split because it's spin-orbit coupling. So what I'm going to do now, I'm going to see, okay, how much is that spin-orbit splitting? How much energy is that? How much are they really apart? I have a number now for the Reupload energy from here to the top, all the way to the top. That's 10 to the minus 18 joules, something like that, right? I want to compare the number now with this splitting. How much is it splitting? A lot, or is it just a little? I just want to know. So that's what I'm going to try to calculate. And in lecture 14, we had an expression for that, which is coming up in the next click. This indicates the transition from n equals 1 to n equals 2. I'm calculating the energy difference, which I can do with this formula, okay? It's the same as we have used before, but now in shorthand writing, HCRH in front, and then the difference between 1 over n squared of one state minus the other state. So 1 over 4, because that is n equals 2 squared, minus n squared when n is 1, which is just 1. And so that is the value of the transition energy between state 1 and state 2, which is this number, which is again just 10 to the minus 18, with a number that is slightly smaller than 2. 2.18 is the total energy you need to put in to get it out, but to excite it from state n equals 1 to state n equals 2, you need, of course, less energy, so that's going to be 1.6 times 10 to the minus 18. And what I'm going to do now is compare this number with the spin-orbit coupling energy splitting. And what I need to do is to use this formula. This formula was derived in lecture 14. It tells me by how much a state is moving in energy because the spin and the orbital angular momenta couple, they combine. You can combine in several ways. This looks like a terrifying formula, but really, honestly, you only have to fill out the quantum numbers and that's it. You just need to know what the quantum numbers are, and that's not so hard. Because the top level of this spin-orbit coupled state, indicated by the p3 halves, that one has a J value, which is 3 halves. That is the quantum number for the total angular momentum. The total angular momentum quantum number is 3 halves when it's in that state. Then the second part is the value of L, which L equals 1, because it's in the P state. And S is always 1 half, because that is the value for the spin angular momentum. In front is 1 half times H times C times this funny A with a little tilde on top. That is a constant. That is a constant that is characteristic for the hydrogen atom. If I'm looking at another atom, this A value will be somewhat different. Okay, so it's an atom-specific value. I know what that value is. I can look it up in a table. I don't have to worry about it right now. So H times C times this A, which I'm looking up in a table, bunch of constants, and then I fill out the quantum numbers when it occupies either one of those states, and then I can calculate for both states and calculate the energy difference. Yes?
So the J number is the number for the excited state, right? For the P goes 3 halves.
Right, so you can see these, if you have not watched lecture 14, and this will look like abracadabra to you, okay? And so, quickly, the 3 half and the 1 half subscripts are the two values for J. J is called the combined angular momentum quantum number, or the total angular momentum quantum number. There's two ways, there's two values for J because you can make two combinations of L and S. L is 1, S is 1 half. But I can make two combinations. In this case, I have one value for L, which is 1, one value for S, which is 1 half, and I can either add or subtract. These two values for J come out. And J can therefore be 3 halves or 1 half. That's it. So that's what the subscript means. The superscript of this P, that is the so-called total spin. The total spin is 2s plus 1. Since S is 1 half, 2s plus 1 is 2. This actually means a doublet. It's a spin doublet. We'll get to it as we move along. The superscript is therefore indicative of the so-called spin multiplicity. So, for hydrogen, you always have a 2 there. If you have 1 electron in hydrogen, it is always a 2 because the spin multiplicity is always 2. 2s plus 1 always equals 2 for hydrogen. Not true for other atoms, but for hydrogen it is. And then the capital P is the so-called total orbital angular momentum. The total orbital angular momentum is just the same as its regular angular momentum in the case of hydrogen because it's only one electron. That means it's the same as this L value, which is 1. And when L equals 1, we say capital P. Because L equals 1 means it's in a P state. And then I make it a capital. So P. The P means it has L equals 1. The 2 means spin multiplicity equals 2. That means spin doublet. Don't worry about it now. But it simply means it has only one value of spin, which is half. So L equals 1 and S equals 1/2. That means that J can have 2 values, 3/2 and 1/2. Those are the 2 states that it can be in, due to angular momentum. So the top state is this, filled out. The top state, which is like P 3/2, 3/2 for J, 1 for L, and 1/2 for S. Fill it out. Really, this is all you have to do, just compute it, and you get 1/2 HCA. Okay, so that is the energy shift of the top state. I'm going to do the same thing for the bottom state. In the bottom state, S is still 1/2, that's the spin quantum number. L is still 1, it's still in the P state. J is now 1/2. Because that's the total angular momentum in that state. And if I do that, I get negative HCA. That's the shift. So basically, the top state goes up by a value 1/2 HCA. The bottom state goes down by a value of HCA. So both are moving away from their original value. That's what this energy means. This energy, ESO, means energy spin orbit. Spin orbit coupling energy, either up or down. So if I calculate the difference between the two, I have to do this. HCA 1/2, which is the value from this, minus this value. Okay? Of course, it's minus now because it's a negative value. So the total value then is this, 3/2 HCA. That is the splitting energy due to the coupling of spin and orbital angular momenta in hydrogen. This is the same value as was presented in lecture 14. The same value was presented there. Now what I'm going to do is I'm going to take that value and just numerically calculate. I'm going to look up what is this value A, and then plug in the numbers, and then this is what I'm getting. Okay? So 3/2 HCA equals this. 7.22 times 10 to the minus 4, not 14, 24 joule. 10 to the minus 24 joule. That is a lot smaller than the transition energy from n equals 1 to n equals 2, which was of the order of 10 to the minus 18. This is 10 to the minus 24. There's 6 orders of magnitude in between. That means 1,000,000 times smaller. So that splitting energy there is 1,000,000 times smaller than the energy difference between state 1 and state 2. Okay? What does that mean? It basically means that it's basically insignificant. Okay? It's very tiny. Don't believe me? Here is the absorption and emission spectrum of the hydrogen atom. It's a measurement. On the top, you can see the absorption spectrum. Every time you see a black line, it means those colors have been absorbed. Those are transition energies of the hydrogen atom. That is where a photon can actually lock or combine 2 states. All the energy differences between the states are potential transition energies, and they correspond to those black lines. This is the emission, which is the opposite of absorption. Okay? Now the background is black because it doesn't emit any photon when there are no transition energies. So instead of now being black, they're now colored because that's the light that comes out. That means that basically now I'm in an excited state in hydrogen, and I'm falling back to the ground state by releasing energy in terms of a photon. Those are the photon energies that can come out. Okay? So, 2 processes, absorption, aka the hydrogen atom absorbs the photon energy, and now I'm going to go from the ground state to a higher state, or any combination from one state to another state. And this is the reverse process. Now I'm in a higher state of hydrogen, and I'm tumbling back to a lower state by emitting a photon. Okay? That's called emission. Emission and absorption. I'm sure you've heard about it before. So, if I'm looking at the energies from here to here, those energies are actually very high energies, so I'm on this side, okay? Those are, from n equals 1 to n equals 2, actually is about 90 nanometers, so there will be a line about here. High energy, that means very low wavelength. And if you ask me how much is the splitting energy, it's 1,000,000 times smaller, right? So that means that if you, for instance, if you look at this particular line, which is transition between high lying states, I think n equals 3 and n equals 4, I believe, this one. Yeah. Oh, and n equals 3 to n equals 2. This line here is actually split. It's actually a doublet. Okay? Because of spin over coupling. But the spin over coupling energy is 1,000,000 times smaller. So you need extremely fine instrumentation to see that. Typically you won't. Okay? So very small effect. And it just looks like one line. It doesn't look like two lines. Yes?
What about excitation? Is that different?
No, same idea. Yeah. So basically, what I'm trying to tell you here is that this spin-over coupling energy is very tiny, and in hydrogen, we really don't have to worry about it too much. So you may wonder then, like, why are we talking about this, right? It turns out, in hydrogen, not so important, because it's very tiny, but it turns out in other atoms, when atoms get heavier metals for instance, it becomes very important. Okay, it scales with basically the charge of the nucleus, the weight of the nucleus, and also the overall spin state of the atom. We'll get into it, what that means. But all those things go up for heavier atoms, and at some point, the spin over coupling energy is actually very significant, of the order of the transition energies between the different end states. So let's see, what does it mean, really, for me to make a quantum mechanical jump from one state to another state with the help of a photon, which can go both ways, right? I can go from a lower state to a higher state, or vice versa, I can go from a higher state to a lower state. What it means is that light comes in, and the atom feels the electromagnetic field. Okay? As you know, the electromagnetic field, the E field, the electric field, can move charges around. You know that. You've done these measurements or seen it in physics classes. If I have two plates, one is plus, one is negative, put a charge in between, say a negative charge, then the charge goes to the positive side. But if I now switch the polarity like that, then the electron moves the other way, right? But an electromagnetic field is kind of that. It's kind of like an electric field value that goes up and down. That's a sinusoidal modulation of an electric field. So what happens is, when it passes the atom, the charges in the atom will go like whoop, 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 whoop. They'll basically follow the field because they're sloshed back and forth. Okay? So what it does, it kind of perturbs the atom. It wiggles the electrons. It also wiggles the nucleus, but it turns out the nucleus is so heavy compared to the electron. The electron is way more responsive than a nucleus. So for all intents and purposes, for now, we can think of it as that the electron is moving along with the electric field, okay, and that the nucleus kind of stays put. So, how can we describe that? Not so difficult. This formula is basically saying that you create a dipole moment. What does that mean? Mu is the value of the dipole moment. E is of course the electron charge, and R is the distance by which you move it away from where it originally was. So let's say the electron sits very nicely in the atom, in its so-called equilibrium position. That's not a fixed position in quantum mechanics, it's kind of like a probability, but that's okay. And now the electric field comes along and kind of like moves it, alright? By a certain distance, R. And the more the electric field moves it to one side, the more of a dipole moment you create. Okay, that makes sense. If I move the electron away from the nucleus, then I get charge separation, and there's a dipole moment between them. That's just how it is. But this mu, of course, is something that is not fixed in time. Because the electric field goes whoa, 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 that means the R is also something that oscillates. Okay? We can do this quantum mechanically too. We can have the dipole operator, or when it concerns the transition dipole operator. And it turns out, and I will not prove this to you, but this will happen at a later time, that we can very nicely describe quantum mechanically what it entails for light to move an electron from one state to another state. You cannot just like move it to any state, it turns out. You can only move it to certain states. And to which state you can move it is defined by this thing here. This is called the transition dipole moment, which is the operator sandwiched between on one side the initial state and on the other side the final state. The wave functions, okay? The operator is in between, and then you integrate over an entirety of space. If you do that, and this integral is not zero, that means that the transition is allowed. Which means you are allowed to move an electron from one state to another state with the help of light. But this is not true for all of these combinations, because many times, or in almost all cases, this integral actually turns out to be zero. Which means transition is not allowed. Transition is not allowed means light is unable to excite it from one state to another state. Doesn't have the capability to do it. This is a short way of writing it in, of course, Bragg-Head notation, which is shorthand writing. So when this thing is non-zero, then transitions are allowed. So tell me now, when is this thing non-zero? Like under which conditions can light excite an electron, let's say from the ground state to another state? To which states can I excite this electron? To just any state, or is there a restriction on it? Turns out there is a restriction on it. The restriction is, the most important restriction is that delta L, the change in orbital momentum quantum number, must be 1. Either +1 or -1, it doesn't matter. So there must be a change in the angular momentum quantum number of the electron when I excite it from one state to another state with light. There's another one, which is a restriction on delta ML, which is 0 or plus -1. Okay? Which is almost automatically fulfilled if you do the top one. So the top one is the most important one. There must be a change in orbital angular momentum quantum number when you excite an electron from one quantum mechanical state to another state. Why is it 1? Well, there's many ways in which you can prove this or interpret this, but one way to get a sense of why this is so is because the quantum number, the spin quantum number, the angular momentum, the intrinsic angular momentum of a photon is 1. Okay? Photon is a specific kind of particle. It's a so-called boson. And this boson has a quantum number which is an integer number. In this case, it's 1. It's a quantum mechanical entity, a photon, which has a spin angular momentum quantum number of 1. And that means when a photon is lost, it's being absorbed the overall momentum must be preserved, and therefore it means that the quantum state of the material needs to change by 1 in terms of angular momentum. So the spin angular momentum of the photon is gone, but that total angular momentum, the total angular momentum of the material state of the atom, has now gained a quantum of 1 in terms of angular momentum. Okay? So the overall angular momentum is preserved. Does that make sense? This is called conservation of angular momentum. So this delta L plus of -1 is there because it's a conservation of angular momentum during the transition, during the interaction between light and matter. Okay, this is a diagram which is terrifying at first, but these are the states in hydrogen, the ground state here, then 2s1, 3s1, now it means the electron is in that state or in the state above it. And then I have the p state, and then on that side I have the d states. The d states are only relevant, of course, for n equals 3. And I'm also indicating the splittings, due to spin-orbit coupling. Spin-orbit coupling is not relevant in the s states, because there s equals 0. The total spin is, actually I shouldn't say that. S is still 1/2. L equals 0 for s. L equals 0 means that the only combination of angular momentum you can have is by s, which is half, so there's only one combination. Therefore, it does not split. But in the p state and in the d state, I can always make 2 combinations. Okay? Because I have one value for L and one value for S, and I can either combine or subtract. Okay? Either adding or subtracting, and that means that I can have 2 values for the total angular momentum, and therefore there's 2 possibilities for the electron to accommodate those states. What I'm showing here to you is the lines connect the transitions that are allowed with the help of light, with the help of photons. And in all of those cases, all of those combinations, delta L equals plus or -1. I cannot go from this state, S, to another S, because there delta L equals 0, which is not allowed. That's why I cannot make this vertical transition up. I can also not go from the 1s to a d state. Okay? Either one of them, there's 2 of them, 2 possibilities, but I cannot go to them because delta L in that case will be 2, which is not allowed. I can only go from an S state to a P state, or from a D state to a P, or an S to P, because in all of those cases delta L equals plus or -1. That's the main message of this slide. Remember that these splitting energies in hydrogen are very tiny. They are exaggerated here. They're not to scale, okay? Basically, you can't see them. Just squint your eyes, pretend they're not there. Let's indicate here for kind of connecting the dots. Yes?
Could you go from 2s1 to 3p1? Is that possible?
Yes. Because there's no restriction on n. Remember? No restriction on n. I can go from top to bottom or bottom to top, also doesn't matter. The only restriction here is delta L. And delta L in the S state, L equals 0. In the P state, L equals 1. So delta L equals 1. Yes?
What is that 2 signifying?
So what?
That 2.
This is spin multiplicity. Okay? Spin multiplicity is 2s plus 1. Spin in hydrogen is always just 1/2, because there's only 1 electron, which is spin 1/2. So 2 1/2 times plus 1 is 2. That means it's a doublet spin state. Again, we'll practice all these so-called term symbols, what they mean, and get used to them. This was introduced in lecture 14. Yes?
Because there's no limit on what entity, can the change in NT 0 involve with changing angular momentum?
In principle, yes. Yeah, in principle, yes. Okay, so I'm showing you another atom, neodymium. Neodymium is a very heavy atom, and it turns out that the A value, that is part of the spin orbit coupling energy, is now significant. you see here a very complicated diagram that you don't have to memorize or do anything with. I'm just pointing something out, okay? So don't worry about this. But you see here on this side, the so-called term symbols. This again is a total spin, so a total angular momentum, which has now very high numbers. This I is now a very high alphabetic number, which means the total orbital momentum, angular momentum, is very high. And the spin multiplicity is also a high number. All of this indicates that there's a whole bunch of electrons that are important, not just one in hydrogen. But if you have a lot of electrons, things get progressively more complicated. That's why those term symbols look more complicated. But the principles remain the same. I can make transitions between different states. And here are in arrows indicated which transitions you can make in this particular atom, this particular element. Right? Not all transitions are allowed because you have to have this delta L condition and there's some other conditions that you have to abide by. But here you see indeed that you can make transitions in a lot of different elements, and neodymium is no exception. Now the neodymium is special because this one here, this transition, okay, from the top state to this state, is a very efficient transition in neodymium. And it's so efficient, in fact, that neodymium is used as a lasing material, okay, in green laser pointers. All green laser pointers are based on neodymium atoms, actually ions, in a glass, an yttrium glass. And what happens is you see the batteries goes into this like pen, all right? Most of this pen is just where the batteries are. The laser itself is very tiny. There's a little, the green little plate there, you can see that's where the energy from the batteries is being translated into a little lasing action, okay? That is an 808 nanometer laser that pumps this kind of, let's say, yellow tube, which is given over here. Right? So what happens is 808 nanometer radiation comes into this little tiny crystal in which the neodymium atoms are. I'm exciting them to a higher excited state, and then I'm going to tumble back this state here, which is the state I just pointed out in the previous slide. That is 1064 nanometers. That is the radiation that comes out, and then that radiation is passing through another material that then converts this 1064 into half the wavelength, which is 532. The 532 is the green. That's the green color that comes out, and that's basically sent in, onto the wall, right? This whole module is just this big, and that's doing all the work. It's a very ingenious thing. In fact, it's like an 808 laser, there is a 1064 laser, and a doubler, all integrated into this little tiny little print board. Okay, so it's a very nice technology, giving you this very nice green laser light that comes out. The bottom line is that the transition that does this is this like heavily spin orbit coupled state. It's so spin orbit coupled that the transitions are actually happening between those states. Very significant, cannot be ignored, as we did in the case of hydrogen. Here it's actually important. It defines the color of the light that comes out. Okay? Yes? You had a question?
No, it was the answer.
Okay. Anytime you use a green laser pointer, just realize that what's happening inside is pure magic. Pure magic, sorry. I was so excited, couldn't even pronounce it. All right, now, last 3 minutes, I'm going to make my first step into the world of atoms that have more than one electron. Mind you, the hydrogen atom is the simplest atom that we have. Just one proton, one electron. The good thing about hydrogen is that we could solve the entire problem mathematically, no approximations made. We get exact results. For instance, we could exactly predict the size of the hydrogen atom. We could exactly predict the ionization energy of the hydrogen atom with quantum mechanics. Not with classical mechanics, but with quantum mechanics we could. Now we're going to take the next atom on the list, helium. Helium, of course, has 2 protons, also has a bunch of neutrons, typically 2. That's the nucleus, and it has 2 electrons. So, compared to hydrogen, a way more complicated system. In hydrogen, this is the Hamiltonian that we dealt with. Okay? we basically use this so-called relative coordinate system, where we only look at the distance between the electron and the nucleus. We didn't think about the center of mass of the entire atom that was floating around. So we only had one relative length scale to deal with. And in that case, we had the potential energy Hamiltonian and the kinetic energy Hamiltonian. Remind, this square, this triangle squared, the del squared, is of course the kinetic energy operator part. The second part on the right, of course, is the potential energy part. This was a problem that could be solved exactly. Okay? And we get these wave functions out. Bless you. Here is the helium atom. Like I said, it's much more complicated. I have many more particles. Right? 2 electrons, 2 protons, and 2 neutrons. If I write down the Hamiltonian, it gets more complicated, folks. All right? What is in this? Several ingredients. I'm going to start all the way on the right. This is the interaction energy between the 2 electrons. These 2 electrons have the same charge and they will repel one another. This is the repulsion potential energy between the 2 electrons. What are the other terms? Well, this one is basically the Hamiltonian as if you were in a hydrogen atom for one of the electrons. Okay, so this is the interaction of the electron with the nucleus plus the kinetic energy of that electron. Electron number 1. But I have 2 electrons, so there's another one. Okay, so there's H1, which is just the kinetic and potential energy of the electron number 1 with the nucleus. H2 is the same for the second electron, its kinetic energy and its interaction with the nucleus. And then, of course, the last term is the mutual interaction between the 2 electrons. So those are the, if I group these things together, I get basically 3 main ingredients. Namely, H1, electron 1, H2, electron 2, and then V12, which is electron 1, electron 2, interacting, aka repelling one another. This is definitely more complicated. Definitely more complicated. So, we cannot solve this analytically without making approximations. We can't. Okay? So we have to be somewhat smart about it and make some approximations. And the first thing I'm going to do is, let's pretend that the electron-electron interaction term is small. Is that true? No, it's not true. But it's a good first step. All right? In that case, I can just cross this one out, the last term. Let's forget about it. Let's first see if we can solve the problem with just H1 and H2, the 2 Hamiltonians for the individual electrons. Okay? So that's what I'm going to do. And in order to solve this problem, I'm going to use this general strategy. I think we've seen it before, but this is a general strategy. If your Hamiltonian is basically having 2 ingredients for 2 different particles, 2 different things, okay, because H1 has nothing to do with H2. There's no mutual interaction between them. That is the last term that I crossed out. This one, H1, is just particle 1, just particle 2. They don't really, there's no cross term in between. That means they're individual. And in that case, I suspect that the solution of the wave function for this Hamiltonian is just the wave function of one times the wave function of another. We've done something similar before. Now if you remember this, we've done something similar with the 2-dimensional box. This direction have nothing to do with one another. This is H1, this is H2, and the wave function is just a product of the individual solutions. Same here. Same kind of idea. Same thing happens also with spin. Spin is completely independent of orbital, so I can just, the total wave function is in that case just the orbital wave function times something that has to do with spin. That's why I can simply make the product, because the Hamiltonians are individual. Yes?
So, if we're doing this approximation, in order to solve the wave function as a whole, we just consider like I have R1 with the H1 operator, and so I have R2 with the H2 operator, and then multiply the results together.
Yeah, I mean, if you put this into the total Hamiltonian, you'll see, actually, it's pretty easy to solve. You'll see it automatically that it just simply rolls out. There's no real magic here happening. Anytime you see a combination of two Hamiltonians that are added, that have nothing to do with one another, this is always a solution. Which is very easy to prove. You can do it. And you'll probably do it in a discussion or in a moment. Okay, this is called the orbital approximation. Okay, so that's a name. And this would be my solution then. I have one wave function for the first particle, another wave function for the second particle. Each of these electrons has their own set of quantum numbers. That's why I say N1 and N2, L1 and L2, and so forth. And the energies that roll out are just the sum of the two individuals. Okay? Just the sum of the two individuals. And that is something I can calculate, because I have the wave function shape now, I have the hydrogen form solutions for the energy, and I can just compute what I expect the energy of these two electrons together to be in the helium atom. What is the total energy that they have? Okay? Yes?
Does this trend hold for like larger approximations for like more than 2 electrons as well?
Yes, I mean this is used in general, not only for helium, but also for other atoms. Correct. We'll see, we'll get into it. Here is just 2, so the electron configuration in ground state for helium will be 1s2, and that basically means that I have to add up the two energies for the individual guys, alright? And I can do that. Remember, this 4 here on top is actually Z, okay? Z squared, which is, you know, 2 squared is 4, okay? So that's why there's a 4 there. But I can add it up, and then get the total energy. The thing that I have, of course, overlooked is this interaction term between the two electrons. And what I can do, and this is definitely an approximation, is just add it after the fact. By computing this. By computing basically this interaction potential energy between the two electrons, sandwich it between the total wave function that I came up with, and call the result of this integral J. That is the correction energy, the electron-electron correction energy that I have to contend with. The total then is this, okay? So what I've done, I have the total energy is just this energy, which is the energy by just simply adding up the two electron energies, but not having them interact. Calculate this integral, the J integral, which is this guy, okay? And then get the total energy. This is an approximation, this is not exact. But it's pretty close. So this whole procedure is a decent recipe for me to get to energies that are somewhat meaningful, okay? So we'll look at this issue as we move along and try to come up with better descriptions than we have over here. All right, 1 minute over time. Good time to stop.